So we're going to walk through calculating a repeated measures ANOVA. So as you can see, we are talking about individuals who have taken a natural supplement, and these individuals were diagnosed with ADHD, and we're looking at their levels of distraction. So each of these are frequencies of distraction, and each person is measured pre-treatment, so prior to treatment, post-treatment, and then again at a follow-up. So the follow-up was 1 month after the post-treatment, which was a treatment for a month. So you have pre-treatment before they start the natural supplement, and then at the end of the post-treatment time, a month of being treated, and then a follow-up a month later. So as you can see, we're going to use alpha 0.05, and because these are the same people in each of these conditions, we're going to be using a repeated measures ANOVA. Okay, so the key is to kind of knowing when to use that repeated measures ANOVA is the fact that they're the same people in each of the groups, and we have more than 2 groups. Otherwise, we would use a repeated t-test. So we're going to start on our typical hypothesis testing steps. And as you can see, I've kind of nicknamed pre-treatment as group 1, post-treatment group 2, and follow-up as group 3, just to use less space on the next slides. So our step 1 is stating those hypotheses. It's as simple as just the null and alternative. I'm just saying that levels of distraction will not differ before treatment with a natural supplement and the 2 post-hoc or post-treatment occasions. Whatever it is that you're showing that there's 2 follow-up occasions and 1 before occasion, and then I'm stating that there is going to be a difference. So state the hypotheses is simple and straightforward. Then we're going to move forward to locating our critical boundary, which is step 2. So I have the original data just kind of condensed as far as group 1, group 2, and group 3. And is what we're going to do is the first thing that I do is I fill in my degrees of freedom immediately. That's what I'm going to work towards first. Completing these degrees of freedom so that I can get my critical value. Because to get the critical value, you're going to look up your F crit using your degrees of freedom between group and degrees of freedom error. So numerator is the between group, error is the or denominator of that kind of hypothetical fraction that they use in that critical table at the back of your textbook. First, so let's work on our degrees of freedom to calculate these. So degrees of freedom for between groups is k minus 1. So we have 3 groups, which is, k is 3 minus 1. So we know, we're going to have 3 minus 1, which equals 2. So we can plug that in. Then we're going to do degrees of freedom person, okay? Or between person. Sorry, between person is what they call it. So that is lowercase n minus 1. So we have 4 people in each of these 3 conditions. So there are 4 people that are participating in the whole study, basically. And so we have n minus 1, that's 4 minus 1, that equals 3. So we can plug our 3 in there. Then our degrees of freedom error for repeated measures is the k minus 1 times n minus 1, that's a lowercase n minus 1. So in our case, I always just multiply the 2 times 3, like that first column times the second column. So we have 2 and 3 times 3. So that's 6. That's our error. And then the degrees of freedom total is that capital N minus 1. How many observations total do we have? That is, we have 12 total because there's 4 observations in each condition, right? Minus 1 equals 11, right? So we have 11 there. Now we have everything that we need. So you're going to look up your critical value and your degrees of freedom between groups, which is 2. That's going to be in the top row. And your degrees of freedom error is in that first column. You're going to look at the light face, 0.05. And you should be getting a critical value of 5.14. So our critical value equals 5.14. So that's what we're going to be testing things at. That's where we're going to find significance. So now that we have step 2 and our critical value accounted for, now we can move on to start calculating our repeated measures Anova. And I'll walk through it step by step with you. So, in step 3 is I typically work on my sums of square total first. So I'm going to work on getting sums of square total. But to get any of the calculations in my Anova table, I'm going to need to get all the basic calculations. So what I'm going to do is walk through and get my sum of x for group 1, my sum of x squared for group 1. I'm going to get my sum of x for group 2, and my sum of x squared for group 2. I'm also going to get the sum of x for group 3 and the sum, sum of x squared for group 3. So go through those and start calculating, and I'll show you what I'm coming up with. I'll write them down. I've got 89 for sum of x for group 1. I got 83 for group 2. I've got 87 for sum of x for group 3. For sum of x squared for group 1, I have 2,145. I'm going to erase this and get some more room here, otherwise I'm going to run out of room. Sum of x squared for group 2 is 1,865. Sum of x squared for group 3, I've got 2,023. But we're also going to need to get our persons totals. So basically P. I always kind of do it as P. So that means we're going to add up each person's total scores. So 13 plus 12 plus 14 is 39. 30 plus 28 plus 29 equals 87. This person's 20 plus 19 plus 19 is 58. And this person's 26 plus 24 plus 25 equals 75. Now, I'm going to take those P scores and I'm going to add them up, basically, or add them up when I'm using my between persons sums of squares. We'll walk through that together. We're going to specifically, that's what those are going to be used for, is just for calculating our sums of square between persons. So let's just forget those for a little while so that we can start calculating our sums of square total first, because that's what I usually work on very first. So I'm just going to write here first. So to get our sums of square total, the equation is the sum of x total squared minus the sum of x total squared over n, capital N. Now, if you'll notice, we need to get totals. So to get the sum of x t total, just add up your three groups' sum of x's. So 89 plus 83 plus 87. And you should get 259. Then you need to get the sum of x total squared. To get that, I just add up the sum of x squared for group 1, 2, and 3. So 2,145 plus 1,865 plus 2,023. And you should get 6,033. So now we have everything we need to calculate that sums of square total. So here's what we're going to get. 6033 minus 259 squared divided by 12, right? Because we have a total size of 12. There's 4 in each condition, 4 observations in each condition. You should end up getting, I'm going to put here, actually I'm going to go back on that and I'm going to put it right here, equals 442.9167. That's the sums of square total. So now we can plug that in. So 442 point, I'm going to round it to 92. How's that? Just for squeezing things in. So now we have our sums of square total. We can move on to the next step, which I usually do the sums of square between groups. So I'm going to do some erasing so that we have some room and we can just keep working on this area. So we're going to do our sums of square between groups next. Getting there. Okay. So, sums of square between groups is the sum of every x squared divided by n minus the same thing again, sum of x total squared divided by n. Okay? So, for that x squared, it's each individual x. So we're going to have 89 squared divided by 4 plus 83 squared divided by 4 plus 87 squared divided by 4. I'm going to take all of that, put little brackets around it because those get all added together for this portion, minus, again, our sum of x total, 259 squared divided by the total n, which is 12. Once you calculate that out, your sums of square between groups, you should be getting 4.6667. So I'm going to just round 4.67 for the sake of this. Okay? So we just got our between groups. Now we can move forward and do the next step, which I would do the between persons as the next step. So let's erase this. My eraser is really slow, bear with me. I'm really just going to erase this first portion, because you'll notice the second portion is the same in this as well. So our sums of square between person is that summation, the sum of p squared divided by k. So that's each person score squared and divided by k, and then minus the sum of x total divided by n. So we're going to bring this down here. So for each person, so we have 39 squared divided by 3, because that's how many groups you have, plus 87 squared divided by 3 plus 58 squared divided by 3 plus 75 squared divided by 3. I put little brackets around that. And then it's minus, again, your 259, that's the total, squared, divided by 12. Okay? Once you get that totaled up, be really careful with your order of operations there. Your between persons should equal 436.25. So we're going to plug that in. Oops, 436.25. Okay? Now we can move on to the next step, which is the last as far as the sums of square. And we're going to get our sums of square error. Let me expand this here. Let's erase this. Sums of square error is easy, but you need all of the others to get it. So our sums of square error equals, let's a little smaller, that's pretty large, okay, is the sums of square error is our sums of square total minus sums of square between groups minus sums of square between persons. So what you calculated over here. So we end up with sums of square total 442.9167 to be accurate, if you remember before we rounded, minus our sums of square between groups 4.6667 minus our sums of square between persons 436.25. 436.25. I'm going to just kind of do this right here. So sums of square error, once you get all that totaled out, should be 1.99997. So 1.99997. We'll just throw that in there. Now we have everything we need to get our mean squares. So I just put basically like a division symbol here. We're going to divide across. 4.67 divided by 2 is 2.3334. Again, divide across. 436.25 divided by 3 is 145.42. And then another division symbol here. 1.9997 divided by 6. I got 0.3333, basically. That's what I put. Now we can calculate our f. So to get f, if you remember, It's the same as with an Anova, it's just you have to skip that row. So it's mean square between group divided by mean square error. So basically, we end up with 2.3334 divided by 0.3333. And you should be getting, it's odd, but an equal number, 7. Our obtained F is 7. Now if you go all the way back to step 2 so we can see is this significant or not, I'm quickly going to erase this area though, so that way we can draw this out. Have a little space to draw. Okay. Let's go back to our step 2. If you look, our critical value is 5.14. So, at 5.14, remember, 5.14, anything beyond that is significant. That's our critical value. Well, our obtained test statistic is 7. You know, that's probably over here somewhere. So F equals 7. So we do have significance. So now we're going to need to calculate an effect size and also post hoc test because it is significant. So we're going to move forward and walk through those steps. Okay, so for effect size, I have my little table here filled in with what we had. It's the sums of square between groups divided by the difference between sums of square total and between persons. So it should look like this, and it's called a partial eta squared. So we have 4.6667 divided by, I'm going to make that longer, 442.92 minus 436.25. Okay, you should be getting, I round it to 0.70 is our effect size. We also need to get our post hoc tests because we found significance. So we're going to use Tukey's HSD, which is that Q times the mean square error over N. We're going to take that square root of that. Now to get Q, we need to find our critical value in that studentized range statistic. That's a quotient. So range is equal to K, which equals 3. Okay? And then we're going to use degrees of freedom error again, which is 6. So you should be getting your quotient as 4.34. That's that critical value. Then your mean square error is 0.3333 divided by 4. You're going to take the square root of that. So if you calculate that out, your HSD equals 1.253. That means the differences between your means needs to be 1.253 or greater. So let's do some erasing so that we have some room to calculate those out. So I'm going to erase our effect size work and just this information, so we can kind of start working on our calculations for HSD. So I'm going to fill this in so at least we can keep track of it. Eta squared, and then we have HSD. So we're going to need to get our means from the 3 original groups. So I'm going to kind of just organize it this way. So group 1, if you remember, is the pre-treatment group. Then group 2 is the post-treatment group. And then group 3 is the follow-up group or condition. So I'm going to get means for each of these. So M of 1, M of 2, and M of 3. So if you go back to the original data, all the way back to where we had calculations, if you get your sum of x's and divide by the sample sizes, you can get your means. So I'll go back so that I can do what I've got. For the pre-group mean, I got 22.25. The post-treatment group, my mean is 20.75. And then for the follow-up group, my mean, is 21.75. So now I can use those means to see the differences if they are larger than my HSD for those post hocs. So the first thing I did is I did mean 1 minus mean 3. And if you take the difference, so 22.25 minus 21.75, group 1 and group 3, I got 0.50. Well, that's less than 1.253, so that's not significant. Then I did group 1 minus group 2. So 22.25 minus 20.75. And I got 1.50. That's larger than 1.253. So that one is significant between group 1 and group 2. Then I'm looking at the difference between group 2 and group 3. So I have group 3 minus group 2, which, when you calculate that out, it's 21.75 minus 20.75, which equals 1. That's less than 1.253. So that's not significant either. So we know that the only significant difference is between the pre and post as far as those distraction scores. So now we have everything we need to write our results. So we have our overall significance, and then we're going to report our post hoc tests. So this is what it should look like, your final results. And this is how I wrote it. It should be something similar, but I stated that repeated measures Anova showed a significant difference in the levels of distraction prior to taking a natural supplement, at post-treatment, and then follow-ups. So I just gave the 3 treatments. Our F obtained with degrees of freedom between an error. P is less than alpha because it's significant. And I reported my effect size. That's the overall Anova. Then you need to report your post hoc results. And I just stated post hoc tests showed that distraction significantly decreased from the pre-treatment to post-treatment, and I provided the means. So it was as simple as that, making sure that you give your direction there of how it differed, because the post hoc tests are going to tell us where and how things differed, and there should be a direction in that one. So we wrapped up everything we need for calculating repeated measures Anova. So you should have the information you need to go ahead and do your hybrid and start studying for the final exam.